Okay, my dear students, now we are go through to deep analysis of the three processes. What is the sampling, quantizing, and the coding could do. So first of all, we have taken an analog signal. As you can see here, that is the function of time. The signal has a function of time, and getting the samples of the analog signal will result to xn. Here you can see that the t has been changed to n. N means the number of samples, and you can see that there is a substantial difference of notation. There is the first bracket function here in the first equation, but there is a third bracket function has been denoted in the second expression. The second expression considered to be the discrete time signal, because we know that when we sample an analog signal, we get the discrete time signal, and discrete time signal can be represented by the third bracket. Okay, as you can see there, the omega has been transferred by theta, the t has been just converted as n, the number of samples, and phi is as it is. So that is the sampling process that I have told you before, that deals with the x-axis, that means that deals with the number of samples. So what will be the allowable ranges in that particular session? Here you can see that that is the fs, that means the sampling frequency. This is pi fs, that means that pi has been multiplied through to the sample frequency, that is the angular frequency, that the range that covers the cos omega t plus phi. And after that, if you just replace this with the discrete function, and you just replace it with the it just replaces the frequency that it deals. So you can find out that fs divided by 2, from minus fs divided to 2 to the plus fs divided by 2. Fs is the sampling frequency, and as we know from sampling theorem, the fs, that means the sampling frequency is always greater than or equal twice of the operating frequency or the masses frequency. That is the sampling theorem, or you can you know that that has been constantly used in the communication sector and communication theory, because from Nyquist bit theory and also sampling rate theory, we consider that the sampling frequency is twice of the greater or equal than twice of the operating frequency. So that's quite evident and individual point, that and a sole point of first conversion technique, that why we are taking sampling as the first process of conversion, because the sole thing is that to reconstruct the analog signal from the digital signal in the demodulation section, in the receiver section, if you want to reconstruct that, you have to transmit the total signal twice as much of its operating frequency, and that will be its sampling frequency. Okay, so it's pretty much important while transmitting a signal. Okay, now my dear students, we are going through to the next part, that why we use the sampling process, that is the process, and what is the sampling theorem. Now clearly look onto the fact, to avoid aliasing, sampling theorem states that the sampling frequency must be greater than or equal to twice the highest frequency present in the analog signal. That means highest frequency present in the analog signal means the highest frequency, the maximum frequency, and we have to just maximum operating frequency, we have to take the twice, that will be greater than or equal, and that should have be the sampling frequency. Okay, there is a point to avoid aliasing. So what is aliasing? What is the aliasing effect? Aliasing is just like the overlapping, or you can say it couldn't meet two. That's not only the overlapping procedure. Aliasing means if there are two bit of signals like that, and it has a bit of 1 and it is bit of 0, just you have to understand for the purpose of understanding the factor. So whenever it goes through to the channel, for the instance of interference, fading and noise, there may be some problem to for reconstruction. That's the transmitter part. If it goes through to the receiver section, so sometimes the signal sparses. That means the pulse wide, the wide of the pulse has been strengthened, has been increased, and also here you can see that there is a big gap between the two pulses. So whether you will not recover the this part, you will not able to reconstruct the whole input signal. Okay, so that's a gap. And another part is that just overlapping. In that part of context, the two signals will overlap each other, and they will miss some data from that point of view that has been overlapped. So that is known as aliasing effect in both two parts. That is the aliasing effect, that is also an aliasing, because there is a certain period that there are no transmission occurs. So that is a problematic scenario. So we have to just get rid of that. Now here we can know that what is aliasing. Aliasing is a phenomenon that occurs when the sampling frequency is lower than the Nyquist rate. Lower than the Nyquist rate means the Nyquist rate is the rate. Nyquist rate is the rate of frequency that is twice and above of the operating frequency, as you know. And this type of phenomenon occurs when the sampling frequency is lower than Nyquist rate. And what is the Nyquist rate? Nyquist rate is twice the maximum frequency component of the analog signal. Here you can see that is also known as Nyquist rate. That is the frequency, but if you just convert to the perspective of time, you can get that will be the Nyquist rate. Okay. Now, what is Nyquist frequency? That is quite opposite to Nyquist rate. Nyquist frequency is a half the sampling frequency of a discrete signal. If sampling frequency is 200 Hz, the Nyquist frequency will be 100 Hz. This is sometimes called the folding frequency of a sampling system. Folding frequency of a sampling system. First of all, just consider a signal go through to 300 Hz from a 300 Hz through to a wireless channel. So we have to transmit the data through the channel with 600 Hz. Okay, then we can clearly reconstruct 600 or more than that, we can reconstruct the signal in the receiver section. But what is the folding frequency? Folding frequency is just the half of the frequency. We will get the 300 Hz or 300 Hz frequency. That is the half of the sampling frequency of a discrete signal. So that is a pictorial definition of sampling and quantizing. As I can say, as I can give you an explanation, and I have already told you that from the x-axis point of view, here you can see from the x-axis point of view, that is the sampling process, and from the y-axis point of view, as you can see here, there are two signals. One is just the analog signal, other one is the pulse signal. We have given the pulse to identify which values will cross through to the analog signal. As you can see here, these square signals cut through to this analog signal. So there are some point of confliction, and these points If we find the points, that will known as the quantizing.